Hi, let's go through the design flow that we have in mind all the time. Okay, the design flow, and this time this optional section 6 in the project design flow. That is what we are going to explain in this video. It is optional and it is not necessary to do that for any project that you have in mind to solve. Alright, there is no need because the idea is to learn how to do it, and once you know it, you can apply it anytime for any project. So there is no need every time that you have a project in mind to finish it as a prototype in the lab. There is no need to do that, or you can do it if you like anytime. Because the idea now is as usual. You see, you have specified the circuit. You have planned your circuit as plan A or plan B or plan C2, I mean using multiple files. Then you have developed the plan that you have in mind. For example, if you had a plan A in mind, you have selected the target chip, and then you have synthesized the circuit and you have inspected the RTL and the technology schematics. Finally, you have probably tested the circuit functionally. You have tested the circuit functionally, you know, the ideal schema, and then perhaps you have even tested it at the gate level. This is also another optional step, but normally we will solve it, okay, because it's interesting and because this one gives us good ideas on how the circuit works and how fast it can compute operations. And now you are here at the step number 6. All right, so the idea of prototyping means placing your circuit, the circuit that you have in mind, in a top architecture. For example, if the circuit is the circuit W, now you have to invent another VHDL file, the circuit W top. And that is for a given board, for example, this one based in a complex PLD from Intel. Or you have to do the same, you see, place the circuit as a component inside a bigger architecture that you will call the same, circuit W top. If you are using, for example, as a target chip an FPGA Max 10 from Intel, right? That's the idea. And because we are talking about multiple VHDL files, pretty much as we did with the test benches. Remember, the test benches was something very similar. The idea was very similar. You had to place your component and the test into a larger architecture that was called the test bench. But this time, that time that, you know, the test bench was closed. There was no input or outputs necessary because the stimulus and the timing diagram that you got as a result was something internal to the VHDL environment. So this time is different. This time the circuit W has to have inputs and outputs, you know, to connect switches or buttons and LEDs, for example. And as you can imagine, the schematic that you have to consider depends on the board. You have a given schematic for the Max 2 micro kit and another schematic for the Max 10 DE10 light board. So every board has its own schematic, something that you have to read by means of the PDF user guide. So in the user guide, you are going to find the specific schematic that you have to take into account now, and the most important, you see, the pin assignments. Which pins of the FPGA are going to be connected to switches or buttons, and which ones are going to be connected to LEDs. So this top architecture is going to be for that adaptation, considering finally that sometimes the schematic is just active law. and you have imagined an active high input. So I mean D1 equal 1 is what you mean, but you see, when you click the button or when you click the switch, what you get is a 0 when clicking. So you need sometimes an inverter and NOT gate to do the job of converting from active low key to active high input. So this is what you have to take into consideration in this video recording, so that in the end we will try that for 2 different boards, meaning that you can do that as many times as you like. Basically, you know, it's going to be continuing the Quartus Prime project, but now adding the information of which pins you have selected as inputs and outputs, and finally generating the configuration file, POV or SOV or bit, depending on the tool extension, so you can download that file for real in the board and see what happens when the circuit that you have invented runs for real. So let's go and proceed with the recording. So we need a plan to continue with the prototyping of the Circuit W. It is the step number 6, as you know very well, the chip programming and lab prototyping. And this is what we are going to do. Basically, we will tailor, you will specify for the Max2 board, we will use some switches and some LEDs so that the circuit will become installed in this board. All right. So this is the layout of the steps that we will solve here. Basically, you know, we have to study first of all the user guide of the board, and then we have to have a schematic. You know, this is a CSD course, so everything has to be around schematics. So it doesn't matter if later we have VHDL files instead of schematics. The first thing that we have to have is, you know, a schematic of what you are pretending here. So look at this. We have a top entity, and inside we have a component and some signals and some gates and some ports, input and output ports. So this is what we have in mind. Okay. So now, after having the schematic, we have to translate it to VHDL, for example, as the circuit W top, and in this way we will have a project that will consist of 2 VHDL files, the circuit W in one hand and the circuit W top in the other. So both are going to be synthesized together. All right. And to do that circuit W top, we have to find something to copy and adapt. For example, because this is a P3 concept, multiple file project, a hierarchical project. Here you see the hierarchy, it's the top, and when you click the top entity and you go inside, you see another component inside along with some signals and gates. So very well, we have to find, for example, in P3 something similar to copy and adapt, some kind of template. For example, the other 4-bit or the MUX8, all of them based in C2 plans, you know, that's the idea. C2 plan is what we call this hierarchical design. And when we have that solved, or more or less solved, we have to continue the Circuit W project, which has been already started, remember? And now we will place it into a new folder, for example, P3 and Circuit W, and the name of the board where it has to go synthesized for, right? So that is the new folder for this new project of chip programming. And then when that is solved and everything works conveniently, we will assign pins, because basically everything goes around pin assignment, and then resynthesize it all so that we can generate the configuration file to be downloaded into the board chip by means of the board programmer, and that depends on every tool. You know, Quartus Prime has a tool for programming, Xilinx has another tool for programming, and Lattice the same. So that's the point. Even depending on the board, you have one kind of programming tool or another. So that is going to be the programmer is going to be depending on the board that you have in hand. So that is the layout, and we will come back here time to time along with the capture of the computer screen showing the several steps to the end. Let's browse the P3 project on arithmetic circuits and multiple file hierarchical VHDL design, the plan C2, in order to find an example to copy and adapt it to be the circuit W top. So here you will find that kind of top files or top entities that has other files inside. For example, here you have the other 4-bit, which is solved. Indeed, any project solved as using the plan C2 can be used for this purpose. So you have here the other 4-bit. You have as well the MUX 8-bit, the same, and even the comparator 1-bit that can be solved using the plan C2, using the method of multiplexers. So this is also possible to be used as the base design. Okay, so why not? Let's go into the comp 1-bit and see what we've got here. We've got the planning, you see, and then in the development section, this is more or less what we want. A top entity with some gates, and then a block that is the component that has to be adapted to the board. So why not open this file, which is the top, right? The comp 1-bit here. If you click it, well, let's not click, simply click, but let's save the link as in the right place, which is this PCL CSD P3 microkit, and save. So now in this folder you have the comparator, and the comparator can be renamed circuit W top. And now it's time for you to investigate how this circuit is built. You can open this file and see what happens. You see? And what you see is the entity name and then the architecture that has several components and some signals. And then there is the beginning of the instantiation of the several components. And you see there is a final section on other equations and circuits. So from this circuit you can go putting what is not necessary. For example, the many chips that you are here can be deleted. You need only a single chip. So there is the need of a single component, the circuit W, and in this way you can personalize this circuit that you've been copying into what you want. So circuit W and the top entity circuit W top. Remember that what you are doing here is simply translating this schematic. Okay, you are translating this schematic into VHDL. This is what you have in mind. Taking an example, never doing that from scratch, but take an example like this comparator 1-bit, which is structured accordingly to the plan C2, and make the convenient modifications. So this is what we have in mind, the circuit W. So now you can say here, well, the port section of this top, okay, what is what you see here? The top section now is, as you see here, D1L, D0L, AL, BL. So the signals are active low. The new ports are going to be active low. So this means that you are going to have D1 active low, D0 active low, then A active low and B active low. Those are the 4 signals to take into account as inputs, and then the output is the same, W active low. So this is in some way the new component to invent, okay, just a variation of the circuit W. Well, it's time as well for replacing this text. So I did that example before, so I've got it saved here in my old version. So I've got the top, so now it's time for you to do that job of editing everything here conveniently. So I can do that now. You see, an example of the step number 6 in the VHDL design flow. So this is the top, you see. I will go and copy directly. So this is my top, you see. Control C. It is pretty much what you've got here, but let me copy it again, because you see there is something else in the schema that you have to take into account. The LEDs that are not going to be for use, the LED 0, the LED 1, the LED 3, the LED 4 are better be connected to logic 1, because a 1 allows that this LED is to be off, no light. So the only LED that will go on and off is going to be the LED 2, which is going to be connected to the WL output of the circuit W chip. The other ones are going to be not used, but you see the new block has these outputs as well. So this is what we are talking about here. The LED 0, the LED 1, the LED 3, and the 4 and many other outputs are going to be outputs for connecting to the corresponding pins of the LEDs that are not used. So that's the top entity. Then the architecture. You see, the architecture is the perfect copy of the component W. So you can very well copy it. Okay. You can copy the circuit, Control C. And this is the component W. The component must not be modified in any way. Look at this, what we are doing here. The component is W, the circuit W, and it is as it is for all the different projects that we've been working. There is always the same component or the same entity. So now, even now that you like to implement it into a real board, you better do not change the component, but invent something like the circuit W top that will handle all the variations, like these logic level adaptations and many other pins. But the chip that you have in mind to test is always the same, circuit W. In the same way it was placed automatically inside a test bench. So now it's the same, the component do not change at all. And now the signals, yes, the signals from this circuit, you see the signals are D1, D0, A and B. You can have the same name for the signal and the same name for the component port. There is not a problem about using the same names, because the component is one thing. You see, it is separated. It is manufactured in another file, and another thing is the schematic that you've got here at this circuit W top layer. So you can use the same name. Why not? So let's use the same names for the signals, pretty much as the test bench did. It was the same idea. So now you can use the same D vector 1 down to 0, A and B and W as the signals to connect to the gates, the NOT gates. So now the instantiation has to be like that, you see? Let's instantiate the circuit W. So you can continue editing the one that you've been copying. You see, the only thing that you have to do is to replace all signals by the new ones that you have in mind. Control C, something like this. And now begin. You see here you had the instantiation of the chip 1, which was a MUX2. not now. You see, now what you have in mind is to instantiate the circuit W. So let's copy it. Okay, so you see this is a command, so you may change that instantiation of the circuit W. So this is what we are going to do here, so you can copy it exactly as it is to your file. And now what is left is the other equations, and here you are the other equations, which are simply from the schema. Remember, you are simply translating an schema. Okay, so you have 5 gates, all of the same type, but inverters, you know, NOTs. So this is what you have to implement now in this way. Control C. So the other equations to consider are those ones. Okay, for example, the WL is not the signal W. Okay, D1, the cable or the wire number 1 on the input D is not the input DL indexed with 1, and so on to the end. Okay, so those are the 4 gates, and what is left here is perhaps nothing else. So yeah, the name of this architecture was, I choose the name Max2 microkit adaptation. So this is the name of the architecture, because you know, if you have another schema, you only have to change this name. For example, for adapting the same circuit later for the D light board, the 10 light board. So this is the circuit, okay? So now you've got your circuit saved in the right project, so you can come back to the project folder, and you have the top and the W, and the top is nothing but, you see, is reflecting exactly the circuit. That is what you've got in mind. So now it's time for running. You see, according to our plan, now we have to start, you see, you have to start the circuit W EDA project in a new folder. Well, we did that. In the new project is the circuit W Max2 microkit, and it's going to be a multiple file, and the name for this new project is going to be circuit W top. It's good to make different projects every time that you have something new in mind. Don't do that thing of copying the basic things that work, which are the W and the test bench. If you like, this is working, so this is what you may like to copy from. You see, this is what I did here. I went to P1 and I went to circuit W, so I take from this project that was working the test bench and the W. So I copied these files in this place, in this new folder for the microkit Max2 board. So now I've got the 3 of them. The 2 that I've been inheriting from the previous project, and the new one that I've got adapting a file that exists in order to generate this schema. So now it's simply time to translate that into the EDA tool and make the system synthesize this top entity. So we'll start the Quartus Prime environment and say File, Project, New Wizard. Next, find the location for this project that you know that is L CSD P3 and circuit W Max kit. And now the name of this project is going to be circuit W top PRJ, and the top entity is basically circuit W top. So you say next, empty project, and now add You see the 3 files are found in this location, so you can add them all, say next, and now you can choose the max2 chip which we have in mind, which is the 2210F324C3. That's the chip that we have in mind, populating the micro kit. So you say next, and now select the same tools as usual, VHDL and Model Sim Altera, next, and here you are, the new project. Okay, so now it's time for, if you like, synthesize the project. Okay, so let's do the job of, you see the 3 files here, the 3 files, so let's see if the device is able to get the full picture of the circuit composed of 2 VHDL files. So let's start the synthesis process now to see if everything is alright, or if we've got some mistakes. For example, when arranging the circuit W top. Let's see what happens in this process of synthesis or analysis and synthesis. We have many warnings here indicating that the unused LEDs has never assigned a value. So let's stop the process and let's do that job of arranging the file. Okay, so we have to go back to the top circuit and do that thing of, you see, there is only the chip and then there is the basic nodes, but nothing else here. So here we have to do such a thing as the LED 0, the LED 1, the LED 3, the 4, the 5, the 6, and the 7 are going to be set to level 1. So in this way, they are going to be all the time assigned to 1, so that they will never go lighting. So after doing that modification, let's hope that there is no other mistake here. So let's save, and after saving this, let's start the synthesis process. So finally we've got 0 errors, and now it's time for watching, inspecting as the tool netlist viewer, inspecting the RTL. Let's see what kind of RTL we've got here, because that is going to be a good indication if everything is alright or not. You see the circuit W connected to AL, BL, with the buffer. You see the knot, and the 2 nodes here. So the nodes are here, you've got the other one. So the 5 nodes are placed correctly, and then you've got the 4 inputs and the single output, and then you've got here many more outputs that all of them are stuck at 1. You see, this is the idea. So very well, and now you see, if you click down here, you see the circuit that you had already designed previously by many methods. So very good, it looks fine. So now what goes next? Okay, what goes next is to generate some extra processing, which is the pin planner. Now that the circuit is more or less rightly finished, we have to go to the pin planner and assign the pins. Where you see the pin planner is a tool like this, when you see the full chip, and down there you see every single input that you've been declaring here. So now it's time for you to annotate simply the location of this pin. For example, I know from the user guide, let me go back to the user guide and inspect it. So remember that the user guide are here in Electronic Devices and Companies. This is an Intel chip. So this is the Thoracic Max 2 microkit, and this is the user manual from which we are extracting the pictures and the information about pins. So in the end, we have here LED switches and clock input. So you click here, and let's see if we can navigate to this place. This is the Altera device. So this is the list of LEDs. Very well. So where are the... Yeah, here. You see? The key 0 and the key 1 and the key 2 and the key 3 happens to be the pin U15 and V15, U14 and B14. So this is what we have in mind in our schema, okay? Remember that the schema was something like this, and this is what we are going to do. The B14, the key 3, is going to be the button 4. So let's do that assignment now by means of this spreadsheet in this tool, which is exactly, where is it here? The pin planner. So this is the L1 is the V14, right? Okay. The D0 is the U14. The A happens to be the V15. And the B is the U15. Then the LEDs, or the W perhaps. The W is the U12. So the W is the U12. Very good. So now what is left is only the remaining LEDs. The LED 0, for example. We can find this information here in this table. So the LED 0 is the U13. The LED 1 is the B13. The LED 3 is the B12. The LED 4, the B5. B5 is not so. So which is the valid location? Yeah, LED 4 is the B5. So it's not accepted at all. So what happens here? It was already assigned. This is not possible because we already had this up there. So if one of the pins is already assigned, you cannot do that double assignment. So the A was wrong. So I see that the A, which is the key 0, is the U15. No, sorry, is the key 1, B15. So this is the B15. Now yes, so this is the B5. Okay, so the LED 5 now is here. The LED 5 is the U5. The LED 6 is the B4. And the LED 7 is the U4. In this way, you have every single pin that you have to use in this application assigned correctly. So now it's time for file, close, and now this information appears in the project as another file, a constraint file, right? So if you see now the list of files, well, it is here, it has been assigned now. So now it's time for processing again the full project. The compilation is successful, and now if you see again, the netlist viewer is the same as before. Okay, and now if you keep an eye on the tool technology map, that's the circuit that you really are going to implement. Okay, and there is another thing that you can do if you like. There is a processing or tools. There is the chip planner that depends on the chip exactly, and sometimes the chip planner is more powerful than others. So this is an idea of the real chip, okay? And you can go zooming. You see there is this light blue, and then there is this strong blue, you see, and here is where you are the circuit located. For example, this is the cell that you are going to use. You see this one is empty, but this one that has a different color is the logic cell which has been occupied by the design. So pretty much everything is here. Here you have an inverter with just the connections, but I guess that here is the logic cell that has the circuit inside. You see exactly. You see every single input, all right, and the output W, which in the end is connected to a given pin. And here you can find even the equation, okay, that has been synthesized. Not D and, but this is not that, this is a little bit complicated because you know that data A, data B, data C, and data B are different names from the ones that you've been using as the top ports. So, well, this is simply just an inspection of the real circuit, okay? So everything looks fine. So now it's time for going to the programmer and trying to figure out if the circuit is being able to be downloaded. So this is what I'm going to do now. You see, assignments has been solved. You see the pin planner has been completed. I see the different netlist viewers, and I see the list of tasks. Okay, so there is only one task left, and this task is the program device. You can click here, or you can click the corresponding tab link here to the programmer. So you see this is the compiler tool, and this is the programmer. So when you click here, you have to be able to connect to the hardware that is going to be used to program the chip. You see now no hardware has been detected or anything. So this is what no hardware. You see hardware setup. I have nothing. So now what I'm going to do is to connect to this computer my board. All right. So once I've connected the board to the computer USB port, now I see that the hardware setting, you see the hardware setting, no hardware, the USB blaster has been detected. So I will select it. Okay, a local device. So close. So now I have my USB blaster. So now I can go and say auto detect. So if I click auto detect, this board, you see, is connected. Now what I can do here is to program this. You see, I simply have to say program and configure the PLD. So this is what I'm going to do now. You will see that it's very simple. If there is, you can do that thing of delete. Let me do it again. Delete all. Okay. So you have nothing in the programmer, okay? So now you can say auto detect, and there is a scanning here of the device connected to the USB, and you've got the micro kit. And now you see the file says none, so now is your turn to find it. You can add a file. Where is this file? So it is in the corresponding folder, right? In the project, you see output files. Okay, you can click output files, and this is the POF. Okay, this is the file extension that Altera uses. So this is the circuit w.pof. You say okay, and this is now the file that you will program and configure in the chip. So here none, you may say delete. So now this is the only chip, and it's going to be configured like this. So if everything is all right, you see, you can say now program or a start programming and configuring. You click that, and in a very few time the board changes the LEDs, and now the LEDs are indicating that the programming is undergoing. So now the programming is finished. Okay, and now what I have to see is the board completely prepared for a final test for real. Let me show you the final result of this prototype. Okay, this is the board that we have in mind, and the one that has been configured with the circuit W. You see in some way or another a line of, a line of push buttons, and now what you see is that all the push buttons are not pressed. Okay, so now you are inputting 0, 0, 0, 0, and in this way you have a min-term because the LED is lighting and the other ones which are in not use are off. This is what you have connected here. And then, for example, if you click the 1, okay, you are inputting 0, 0, 0, 1, and this is another min-term, so the LED is still lighting. But when you click 0, 0, 1, 0, okay, like now, you have a max term, because the 0, 0, 1, 0 is the max term 2 in this circuit, so you have a 0, so the LED has a stop lighting. And then when you click the 2 and the 3, in the same way you have another time, it is difficult, you see you have another time a max term. And the same when you are clicking the 3 of them. So if you click simultaneously 0, 1, 0, 1, 1, 1, you have the max term 7, and so on. The other combination, except that the number 10, perhaps this is the number 10, that one is again another max term. So the circuit is really working for real, and that's the experiment. If you have another board, like the FPGA Max 10, the D10 light board, you can do the same thing, exactly the same thing, changing the name of the folder, circuit W Max 10 D10 light, and then you can use or reuse the same name for the project, circuit W top project. In this way, the only thing for you again is to study the user guide of this new board and find which pins you have to attach to every signal of your interest, and keep an eye on the hardware associated to the inputs and outputs to see whether these signals are active high or active low. For example, for this new board, the switches, this new board has switches, the board that you have now in mind, for example, is this one, the Thoracic D10 Lite. So this board has some switches. Instead of single push buttons from the one that we've been using now, you have now a long list of switches. So you can very well set a 1 and a 0 simply sliding the switch up and down, and you have up to 10 LEDs. So it's going to be a good practice, the same as before, switching off all the LEDs which are not of interest. But you have to click to the user manual to see whether these LEDs and whether these switches are active high or active low, or common cathode or common anode. So you will know, inspecting the user manual, which is the right level to drive the inputs, to take information from the inputs and to drive the outputs. Okay, so you can do that very well here. And so there is nothing else to say. It's simply a repetition of the same experiment. Okay, draw the schematic. Draw the schematic. The schematic is different because the board is another one. Okay, for example, this time you have to attach all the not used LEDs to a 0 because they are connected like this with a common cathode. so they are active high, so there is no need for a NOT here. So the port of the CKW top can be the same as the CKW, WW. So the same with the inputs, because it's simply a slide switch. There is no need for using a NOT, and so on. Okay, so after having the schema, you can translate that schema the same way that we did before. Now it is even easier because you have the same schema for another board. So this is the one that you have to take here, okay? And start a new project and assign pins after having synthesized it. Okay, assign pins using the pin planner, and finally use, in this case, probably the same programmer that will detect the FPGA Max 10 instead of the complex PLD Max 2, and so you will be able to download exactly the same way the same project CKW to another hardware. And that is exactly the same if you are changing from Intel to Xilinx to Lattice. And here in this digsys web you have several examples of this final realization of the prototype using one or another board. Okay? So I will supply with this recording the two projects. Okay? The one which is stored into CKW Max 10 DE10 and the one that was stored in the CKW Max 2 micro kit. So in this way you can experiment by yourselves, simply copying my files or revising the information that has gone through this tutorial. Thank you. And you can do the same if you are changing the hardware, For example, this time is another board. It is the same project but based on the board D10 Lite, okay, which is quite the same. You have an array, you have a line of switches, ones and zeros, and then you have a line of LEDs, and then here you have some 7-segment displays that you can use in other projects. But now what you've got is the circuit W. So I guess that if you are clicking 0, 0, 0, 0, you have a 1 in the LED 2. But then if you are clicking 0, 0, 1, 0, you have a 0. Or if you are clicking 1 and 0, 1, 1, 0, 0, 1, 1 is the 3, is another 0, and so on. So you can try this way easy because the switch has memory, so you are not necessary. It is not necessary that you go clicking because the switch can handle a 0 and a 1 permanently. So in this way you can try all the 16 combinations. For example, the number 8 now or the number 10 when you will see that the max term is here, okay? And that's the experiment for the max 10. So this means that in order to download the program into this board, you had to invent a similar example diagram that you are going to call it the same, CKW top VHD, but now it is a Max 10 chip. So the connections, perhaps after studying the user guide, are going to be different, because in this board, for example, you see the switches, okay, and you see that the LEDs are active high. So this time for this Max 10 prototype there is no need of the inverters, for example, but you have to connect still all the LEDs that are not going to be used, for example, to the convenient level, this time a 0, because they are, as I say, active high, and with a 0 they will remain off. So that's the idea of generating a prototype after having gone through the full design process. So in the end, what is left is the report, where using pen and paper and several sheets of paper you can arrange your diagrams, schematics and your text. You can use computer printed results and VHDL listing files, and etc. Whatever resource that you have printed or scanned or commented with your pen tablet. So in the end you have a report that you can submit correctly at the Atenea platform. So this is more or less what I have to say about this idea of circuit prototyping. So what we are going to do here in this digsys course is to go through 1, 2, 3, and 4, and 5, and sometimes 5, this way for the most of the projects, and time to time in class we will show you some prototypes. Okay, we will show you some prototypes like those ones here, so you will be able to see for real how it goes, whatever it is, a counter or a matrix encoder or an RS232 transmitter, whatever we have in mind to design, it's going to be like this. For you, 1, 2, 3, 4, and 5, and then time to time, just a real prototyping. That means, as you see, using the pin assignment tool, this is the new thing here, which means basically opening a spreadsheet and simply assigning every input to the corresponding pin. That is what you do, whatever it is the board that you have on the table. And once you've been done that, you simply recompile it all, so the machine generates the corresponding binary configuration file to be downloaded into the platform. But in which way? By means of the programmer. So you simply open the tab of the programmer, you click the tab programmer, and you will see how the board is detected, and then so you will be able to attach to the FPGA the corresponding configuration file and click download or program or start programming. In this way you will have the circuit for real, whatever it is, something that simple composed of us just 10 gates, or something very complex, as much complex as you like. Okay, that's the idea here. Fortunately, this hardware, just to tell you that in the end, this hardware adaptation and this hardware discovery tool, this is possible because it is the typical USB, and in the lab, because in the lab the computers are connected to the virtual desktop. If you are working in the lab, this hardware will be detected correctly, and you will be able to download your experiments as well if you ask for this kind of boards that we can lend to you in some way or another. So you can ask for the board if you like to go through the end of the prototyping stage, because you can do that locally if you have downloaded the Quartus Prime tool in your computer, or if you are in the lab 129 and through the Rabada environment, the virtual desktop, you do the same job of detecting the hardware and downloading the configuration file. So that's the typical experiment that go from the very beginning to the end.